those of you that were in Pete's keynote this morning heard, the ability to do computer vision processing, both traditional and deep learning based, it kind of blows my mind over the years that I've been involved with the Alliance to see how it's proliferated, how it's migrated from very high-end processors down into very mainstream devices. And what we're going to hear about is definitely one case study example of that. Manisha Agrawal has been a software applications engineer with TI since 2006, 17 years of experience in end-to-end signal chain processing of video applications. And what she's going to talk about is TI's deep learning solution on the AM57 Sitara processors for smart factories. Thank you.
Thanks, Mike. Hello, everyone. Okay, yeah. So agenda for my presentation today is that we will look into overview of smart factory. Then we will look into why Sitara processors for smart factories, key differentiation that it brings to the plate. Then we will look into the programming models for programming Sitara processors for enabling the machine learning inference. After that, we are going to look into how to get started using Sitara machine learning on Sitara processors. And finally, we are going to look at third-party ecosystem. So what is smart factory? So smart factory is another name for Industry 4.0 or Industrial Internet of Things. In this, in the smart factories, basically it's nothing but a network of devices connected via communication technologies to form systems that monitor, collect, exchange, and analyze data. So tons of data being generated in smart factories, which makes it perfect for machine learning applications. It is based on 4 design principles, which lay the foundation for the key technology need that these smart factories need. So first design principle is interconnection, where all the devices, machines, sensors, and people are connected to each other via Internet of Things or Internet of People. Next is the information transparency, where the system creates a virtual copy of the cyber-physical world through sensor data. Third is the technical assistance. So here, the system should be able to assist human in making decisions and solving problems, as well as ability to assist them in doing difficult tasks or unsafe for human beings. Finally, it is the fourth design principle is the decentralized decisions, where the cyber-physical system should be able to make small decisions autonomously. So these 4 design principles lay down the foundation for the key technology considerations, such as industrial communication protocol. So the devices connect to each other and talk to each other over a protocol, which is not one single, but there are several protocols that have evolved over a period of time, and they have some strict timing constraints. The nature of the work in the factory floor requires the system to be able to do real-time control of the cyber-physical world. These applications or the devices also need to be having security and functional safety requirements. Along with that, to be able to do the technical assistance and be able to have the autonomous decisions, these devices need to have the ability to do machine learning at the edge or maybe at the cloud. Because these are industrial applications, they need to have enhanced reliability. As well, the devices should be having a longer life. So with that, we look into how Sitara processors are enabling the smart factories. Sitara processors are suitable to be applied in industrial robots for automated sorting. They can do vision, computer, and optical inspection related tasks, are suitable for automated guided vehicles, enabling smart HMI, which is teaching operators. In the smart factories, now the equipments are doing their optimizations by themselves, and there is no longer a need to send an expert to the factory floor for the settings. For the autonomous decisions, all these devices are able to communicate when they need product maintenance. So they are able to flag if there are any anomaly in their operation or what is the remaining useful life of the devices. They are also applied to classify and recognize the sounds and the audio patterns, track, identify, count people and objects. Finally, since there are so much of data being generated by all the devices, and it is layered in field, operator, and the control level devices. There is a need to extract meaningful information from these gathered data through the data aggregators. So machine learning is also applied there. So what are the key differentiation features of Sitara processors which makes it suitable for the smart factories? Sitara processors are highly integrated processors where they support multiple industrial communication protocols on one platform. So traditionally, the problem was solved with the help of an FPGA. So there's a processor to do the main task, but the communication protocols, since there are a wide variety of them, they were solved through the FPGA. Sitara processor brought them together in one single solution in a platform where it supports real-time communication protocols for all the available standards. Then there is in the Sitara processors, there is a subsystem which is called as a programmable real-time logic units that helps to do the real-time control and processing required to control in microseconds or nanoseconds of the frequencies. Along with that, for the machine learning processing, we have specialized accelerators, as well along with that, the multimedia accelerator on some of our processors. That brings an advanced integration for enhanced functionality, such as enabling machine learning inference at the edge for many of the vision applications, as well doing the predictive maintenance at the edge for the field, controller, or the operator level devices. We have natively CSI2 and parallel interface for camera connections on the devices having the machine learning accelerators and the multimedia capabilities. Along with that, some of the platforms, most of the platforms have the PCIe USB 3 SATA connectivity standards. Being the industrial grade chip, they support enhanced reliability, wherein extended temperature and high voltage I/O, low failure in time, and low power on hours. All this solution with the integrated processings that enables lower the system overall system power, and doing it at the edge helps to lower the latency. Along with that, we have the family of devices which are scalable. Our software are scalable across the portfolio, entire portfolio, wherein you can reuse the software across platforms using the TI's processor software development kit. The support is available on ti.com, where technical documentations, the technical reference design on Sitara machine learning can be found. And the experts can be directly seeked with the right technical subject matter experts over e2e.ti.com. So let's have a quick look at the Sitara ARM processor family. At the left side, we have the single core Cortex A8 and A9 processors, which have the PRU subsystems and all other features that I spoke about are required for the industrial applications are supported by all the processors here I'm showing on the portfolio. The enhanced or the accelerated machine learning and the accelerated compression engine is available on the AM57X family of devices. So we have AM5729 device, which is our highest performing machine learning device, which has 4 specialized machine learning accelerator. We call them embedded vision engine, targeted for vision applications. On the AM5749 device, we have 2 of such accelerators. Along with that, in the AM57 family, it is basically a single core and dual core Cortex A15 and C66X DSP core. So all these cores are also able to do accelerated machine learning. Our power consumptions on the specialized accelerators are in the range of 200 milliwatts. So the embedded, the Eve subsystem that I'm talking about, it consumes 2 cores of the Eve subsystem, it consumes 200 milliwatts. And we also have functional safety integrated in our, the current generation of device, which is AM654. So let's look into the programmability of our processor for running the machine learning inference at the edge. We call it Sitara machine learning. Today it comprises of 2 frameworks. First is TI deep learning framework. This framework is suitable for AM57X device. It helps accelerating the layers and operators on the C66X DSP core, and the embedded vision engine subsystem, which is a specialized machine learning accelerator. For all other processors, which is the AM335, AM5, AM4, AM5, and AM6 families, to run the machine learning inference on the Cortex Cortex ARM, we enable it through the ARM Neural Network SDK. So as you can see in this picture here, it is demonstrating the development flow for the TI deep learning framework. It is a 3-step process where you train your network model on the cloud or the desktop. The format that is accepted by the TI deep learning framework is the graph format generated through the TensorFlow, or the Caffe framework and its derivatives, or anything generated using the Onyx format. Caffe Jacinto you're seeing here in this picture is TI's variants of the Caffe framework, where we have added additional tools, something called sparsity. The sparsity is very popular tool, which is suitable to develop a network model for the embedded-friendly devices. This sparsity tool helps us give up to 4x improvement in the performance for running the inference engine at the edge. So the TI deep learning software framework consists of a converter tool. So after you have trained your network model and generated a graph in one of the format, the TIDL import tool converts into a format which is acceptable by the TIDL framework that runs the inference. This import tool is able to do the quantization weight with the 4 to 12-bit accuracy. So we run the inference in a fixed point solution. The activation layers are dynamically quantized while running the inference with an 8-bit accuracy, while the accumulation happens with the 40-bit accuracy. So once the model is imported in a fixed point solution, it can be run on the Sitara processor using a TIDL API. So TIDL API is a wrapper over OpenCL. It's a C++ based API of 5 classes. And it enables running the offloading the layers or the operators on our accelerators, DSP and Eve subsystem, using the OpenCL framework underneath and the libraries that run on the DSP and Eve subsystem. So from the user perspective, they don't need to worry about any knowledge or knowing of these programming of these accelerators. Everything is taken care by the TIDL API just by a 5 simple function call. So the TIDL APIs can be integrated into other frameworks such as OpenCV, and they provide common host abstraction layer. So with the same API, you are able to run on DSP or the Eve subsystem, and there are multiple cores of them on our flavor of devices. So you can have a device having 1 single DSP core, all the way to a device having 4 Eve subsystem and 2 DSP cores. So there's a range of accelerations available, and the complexity, everything is all handled by the TIDL API in terms of running the layers underneath on those accelerators. Along with providing the software framework to deploy the network on the Sitara devices, we also provide several example network models. Those are tuned and developed for the embedded-friendly processors. So there are 3 different models that we provide, one for object classification, another for classification and detection, and third for pixel-level semantic segmentation. These network models take advantage of the complexity reductions and the sparse convolutions. Along with that, the fixed point quantizations. And what we see there's a performance improvement up to 4x or more than that, with a very minor reduction in accuracy. So let's look into the performance of the validated network model. So before my presentation, the gentleman here was talking like how the popular network models are designed to win the competition. They are not suitable for the embedded processors. Similarly, which is true for everyone. So here what I'm showing is the performance of the MobileNet, SqueezeNet, and InceptionNet network models, which are the open source network model, along with the TI provided example network models. So we can see that the TI network models, they have 64 ROIs per second they can perform for the object classification compared to MobileNet, which can do 7.3 ROIs per second. So AM5729 is our highest processing device, which has the 4 Eve subsystem and 2 DSP core. So in our running of those models, we are just using one single DSP core and the 4 Eve subsystem here. On the AM5749, the performance is kind of a half of what you get on AM5729. And then on the other processor, which are not 49 and 29, but other derivatives, they only have the DSP cores. So the models can run on the DSP or the ARM core. So how can you get started with machine learning, Sitara machine learning? There are 2 ways that you can get started. First is you can start with the industrial development kit. We call it AM574X industrial development board. It has AM5749 processor, thereby it has 2 Eve subsystem. But if you are looking to start development with the highest performing device, which is AM5729, then there is a BeagleBone AI board, which is a palm size board, and it will be available in the 3rd quarter 2019. It has 4 Eve subsystem, and it comes with all the benefits that the community bring, if you are aware of BeagleBone Black. So that would be your starting point. For the software and the documentation requirement and all other things, you can download them once you visit the Sitara machine learning page. Our third-party ecosystem, we have partnered with CrossCompass, PathPartner, D3 Engineering, and ATM Systems. They can help you develop network models and deploy on our platform, including doing the performance optimization specifically for the Eve subsystem. Here are some of the useful resources that you can go to our website and look into downloading our SDKs or learning how to start with the Sitara machine learning. Our software development kit, look into the documentation. We have a TI design, reference design on the TI deep learning software framework. So you can refer to that reference design if you are looking to start developing on our platform. I can take questions.
Good job. See, you finished early. So again, direct your attention to the microphones in the center of the room. I will start. So TI was a founding member of the Embedded Vision Alliance back in 2011. So I've seen a lot of different architectures from TI, different cores, right? Optimized for various tasks, including computer vision. And targeting different applications, right? And generations worth of those cores and chips over time as well. So we talked about products for industrial, right? I know that there's also an automotive product line, right? There may be other, either in research and development or productized platforms for other applications as well. Can you talk about sort of the broader diversity of products for computer vision within TI, and maybe to what degree they cross-pollinate each other?
Sure, right. I guess TI's journey started for vision processing maybe before I was born. The OMAP processors were our initial processors targeted for the vision processings. They were popular in the mobile space. After the OMAP processors, we had 2 product line families. Those took the technology from the OMAP processors in the vision space. One is the Sitara processor line that we are seeing here, and other is the Jacinto processors, which is suitable for the ADAS applications. And now both these product lines shares the IPs underneath. So all the R&D work that goes on the ADAS family or suitable for the automotive processing is being utilized on our Sitara processors line.
Okay, thank you.
Thank you.
Questions from the audience? Yep.
Thank you for the and the great presentation. I noticed you have ARM and N support on your boards. Have you experimented, or do you plan to provide access to the DSP components of your boards through ARM and N? Because I see at the moment you have 2 different APIs, one for the DSP, one for the CPU. Have you thought about putting the DSP under ARM and N and then giving a single abstraction?
Right. So going forward, what we are looking or exploring at this moment is using the compiler, open source compiler framework, such as the TVM or the GLOW, right? So we are exploring to have that as a open source inference engine framework, where the objective would be that any network model, are able to run on ARM. And underneath, depending on which processors you have chosen, the processors knows which hardware accelerators it is capable of accelerating which layers. So that would be abstracted using the TIDL API stuffs, yeah.
Do you know Tim?
Sorry?
Do you know Tim? Tim's from ARM. You guys should get to know each other.
Okay. Oh, I didn't know. Okay, yeah. Thank you.
Any other questions from the audience? Going once? Going twice? Everybody's hungry for lunch. All right, we're done. Good job.